SwayamPrabha. Digital India. Educated India.
Yeah, how do you calculate volume? Okay. So, the general expression what we derived in the earlier class was T equal to C A naught integral 0 to x a dx a by minus R A, yeah, for constant system, otherwise it is 1 plus yeah. So, that V equal to V naught, I think that also we will discuss later. So, this is the general expression. If it is constant volume, then epsilon equal to 0. Okay. So, that is why this becomes 1 and this becomes simply minus R A. So, then here we do not have specifically volume coming out from the rate, the design expression, whereas if you derive later, because you know already, that is why I am telling. So, you already seen that for mixed flow reactor and plug flow reactor, you get volume as V by F A naught equal to, right. So, for similarity, I will also write this one as T by C A naught equal to 0 to x a dx a by minus R A, general, I think, for constant systems, let us say, right. So, T by C A naught, this is the general expression for a batch reactor, which you are supposed to remember all the time. Okay. But what we have been thinking was that this T or this equation does not contain volume, but finally we have to design the volume of the batch reactor. How do you calculate volume? What do you know before starting all this reactor design? So, do you have any information? You just remember that our diagram. Production means your F A naught supposed to be, if it is a flow rate, okay, but here there is no flow, but still you know what is the production rate. Okay. You know what is the production rate. Let me tell you, just I think for simplicity, I have to produce production rate, I have to produce 24 tons per day, right. So, I could have divided, I would have calculated per year how much I have to produce, then per day I calculated, I got 24 tons per day, and 24 I have taken because easy for calculations, right. Yeah, but my this design expression will not tell me what is the volume required to produce 24 tons per day. How do I calculate what is the volume of the reactor from this information 24 tons per day and time? C A naught I know, okay, that area under the curve I will, this area under the curve I will evaluate and then find what is T. Yeah, that is what I did, no amount of from conversion, let us say for 90% conversion if I take, or 99% conversion, this equation gives me only time, correct, no, that area under the curve when I take, I have to take either 99% conversion, 95% conversion or so, whatever, because you know that from 95 to 99, okay, let me also draw that, this is general shape only we are, general shape only I am just drawing. So, normally you will get most of the time like this, and here you see why it is steeply increasing.
1 by minus R A.
What is R A at x equal to 1? At 100% conversion, what is R mathematically? 0. But what is this coordinate? 1 by
infinity.
We have to go to infinity. And now just imagine before that it is not 1, 0.99999, then you are very close to infinity, right. So, that is why if you now come back a little bit slowly down this way, then you know that lot of area increase will be there in this region, whereas here I will not have that much increase. That is where the economics in designing the reactor will come, because I may go to 99.499999, okay. I need very large volume when compared to 99.9929. There will be tremendous difference between these two. So that means only to produce 0.09, okay, 0.99, 4 nines, only I have taken 2 nines now. So then you will have point another 0.1. So to produce that small amount, then I have to go for very big volume. No engineer will do like that. Are you able to follow me, or you able to follow me? No, because 0.99, 0.999, 0.999, every time when you are moving one decimal, your volume also not 10 times increasing, it is sometimes 100 times increasing, because it is very steep going to infinity. Okay, here, and theoretically speaking, when 0.9999, if you put 100 nines, then you get infinity. Again my same thing, if you have infinite volume, you cannot operate the reactor, because the entire universe is only one reactor, your reactor. So that is the reason why always you have to design, whether you have to decide what is the economically viable volume or conversion. Conversion only gives you that volume, right. So that means you have to decide, okay, now 99% is fine with me, conversion, right. So that is why conversion is always coming there. So I am now taking till here, let us say, okay, that may be 0.99 or maybe 0.98, right. As an engineer you have to find out which is the viable one. Okay, so this is XA final. So knowing this information, let me say that, okay, I will also give you this area under the curve T by Ca naught, and even if I take, I know Ca some value, so the T is, let us say, 7 hours. Now you tell me, how do I calculate? That means to produce, I do not know how much amount now, because batch will not tell you what is the amount you have to produce. Whether you take 1 kilo, 1 ton, 100 tons, time is same. That is the beauty with this reactor. But now you have to find out what is the volume depending on production rate. Okay, can you guess? You have to also try to imagine, maybe a wrong imagination also no problem for us. You should be able to imagine and then tell us that, sir, this is what I am thinking. If it is wrong, I will tell you. If it is right, no, I will appreciate you. Even if you tell wrong, I don't scold you. Okay. Yeah.
Multiplying production rate with time.
With the time? Okay. What do I get when I multiply 7 into 24?
Mass.
Divided by 20.
So I am getting that tons only, so 24 tons. 24 into 7 tons.
7 tons. 7 tons.
24 into 7.
24 by 24.
24 into 7.
24 into
24 into 7 by 24.
Whatever.
7 hours I have.
Yeah,
Ah,
how much
per day,
mass
yeah.
we are getting.
Day is converted into hours.
Oh,
Tons.
7 tons.
24
Okay.
by 20.
okay. First of all, you have not asked me one question. You know, this time 7 hours, that is the only time you use for calculation?
Between two batches.
Yeah, you have other timings also. First of all, you have to take into account. That is why we say that this is what is called TRX. That is only reaction time. See, the total batch time, T batch, will be TRXN reaction time plus, see, you have to first charge when you are first starting the reaction, right, that charging time. Then after the reaction you have discharging time, and again sometimes you may have to clean, so cleaning time, all those timings also will come into picture. You know, particularly biochemical reactions, they use sterilization time, otherwise next microorganisms may die. Okay, and I told you batch reactors we choose because we also have that flexibility in products. So the earlier products may contaminate the present batch, so that is why I have to clean it there. So all those timings will come into picture. That is T, what you call, no, not cleaning, first one what you said, loading, charging, okay, CH, and also you have T discharge, DCH, plus T cleaning. Anything else? Generally these things. Okay, all the timing should be known to us, but here we can have some kind of optimization. If your operators are very good, very efficient people, then probably all these things will be in 1 hour you can finish. Okay? Or if there are very lazy people, then it may take 2 hours. So, okay, so because if you do not have particularly automation and all that, if you have automation, then you are replacing humans with machines. Machines are always efficient when compared to humans. Okay? So, I mean in doing general work, okay, day to day work, but when you want to use brain, humans are the greatest. Okay? So, that is there. So, all this is 1 hour and this is 7 hours. So, now I have total batch time 8 hours. Okay? So, now what we do is I have to now produce 24 tons per day, but I have now 8 hours per batch. Okay. Yeah, how many batches we can now take? 3 batches. Okay. So, now when I have 3 batches, okay, so in this case 3 batches, number of batches, number of 3. So, now per batch how many tons? Yeah, per batch you have now 24 by 3 tons per day. So, sorry, no, 3 batches and each batch will have 8 tons. This is tons only, 8 tons. Okay, now how do I put this? I mean, how do I now calculate the volume? Yeah, you know the density of the reaction mixture. Okay, so when you have that density of reaction mixture 8 tons, let us say water. You now tell me what is the volume? I have exactly like water, like reaction mixture. 8 meter cube, because 1 ton per 1 meter cube, 1000 kgs, no, 1000 kg per meter cube, right? So that means 1 ton per meter cube. So I have to have now 8 meter cube volume, and our problem is not yet over. This 8 meter cubed volume I have. How do I now put that one as a physical reactor? That means you should have some diameter and some length. Huh? That comes later, but how do I put this? What is the shape? Because if I am a crazy fellow, I can take 1 nanometer and length, because 8 meter cubed I can put anyway, no? Now you can calculate what is the length. I think it goes to Mars or maybe Jupiter or beyond that. That is not engineering. Okay, we know that. Then what else? I can take diameter of the earth and then calculate height. What will be the height? 0. So again, where do you put? So what is logical now? Engineering logical. Huh? What is thumb rule?
Like some
L by D equal to what?
1 by D equal to 1.
Janvi, say something.
1.
Tell.
1.
Huh? 0.75. 1.
1.
2. Okay.
1 to 1.
L by D. I am asking L by D because L by D you have to fix. 2 extremes I told. You can take 1 nanometer, almost 0, and then length you can calculate. Not practical. You can take diameter of the earth and then also calculate height. The diameter of the earth is equivalent to your tank diameter. Okay. So then you can calculate height. Okay, that is also 0. So these two are not engineering solutions. So what is engineering solution for fixing L by D? He says 0.75, you say 2. Why do you say 2? I will also ask him. Yeah, she says, Pooja says 1. Huh?
We should choose such an L by D where the reactor surface area is.
You can never have that kind of thing, no, because surface area per unit volume, only sphere has minimum. So all our reactors are
Ideally,
should not be. So our reactors are cylindrical.
As the L by D ratio changes, non-ideality increases.
What non-reality?
Dead zones.
So what?
Mixing
Okay,
will
they
be
have
conversion.
what will happen?
Conversion will be affected.
Why conversion changes if dead zones are there?
Proper mixing will not take place. Some portion of the reactor won't mix.
How do you avoid that? Stirring. So now fluid mechanics again will tell you, generally for L by D equal to 1, you have good mixing. See, when you have this tank, so when you put this kind of thing L by D equal to approximately 1, one stirrer is enough, and when you go to L by D equal to 2, then you know sometimes you also seen like this, right. So, general thumb rule is for each L by D you need one type of blade. You know, normally we have so many things, we have propeller type stirrers, we have turbine type stirrers, anchor type stirrers, all these things are there. So, we know approximately in all these things L by D equal to 1 will give me good mixing. That means, in this case I should see everywhere uniform concentration and temperature. Even if I take L by D equal to 2, many times you will take L by D equal to 2. Okay. You know, you would have seen batch reactors, but it is not L by D equal to 1 most of the time. It is L by D equal to 2 many times, 3 rarely. That means, you know, stirring is not that efficient, but L by D equal to 1.5 also is common. But criteria is that this L by D should be such that your mixing should not be sacrificed, mixing should be perfect. That is the engineering rule. Okay. So, now I think I am able to make, you know, some clarity where you have to remember these simple things, they are not complicated. We are not really discussing that kind of complicated where we will get Nobel Prize. No one will give us Nobel Prize for us, you know, when you take L by D equal to 1. Okay. But we should know why we are taking L by D equal to 1, right. So, if someone asks, okay, I think, you know, why did you say 0.75?
Because if there is that is diameter size, the reactor most stable can stand. So, just have to practical guess.
Why standing? I think standing depends on our structure, where you know you put that legs and all that.
Bottom of the area is high, it will be better to.
No, cylinders only, no. Cylinders only. Most of the time we go for cylinders. Okay, which size you go other than cylinders? You tell me. Why again? That is also engineering question. Why do you go most of the time for cylinders rather than spheres? Very difficult to fabricate, very difficult to construct. Okay. So, that much again we do not want to spend our time and all that. Simple thing is take a big like this, like this a sheet and then fold it. Put one thing here, put another thing there, not permanently, because you have to charge and all that. No. So, that is all. That is very simple, because engineers will think, as I told you, in a simplest manner. That is the reason why you have to, oh my God. Okay. So, this is what. So, now you know how to calculate volume of the thing. I will give you a problem, maybe I will upload, or maybe tomorrow I will give on a piece of paper and then distribute to you. You solve that problem. It is a very good problem, but it is a reversible reaction, because now you know this R, it can be either irreversible reaction or it can be reversible reaction with some orders or without order. All kinds of complicated equations can come. So, that is why, because you already exposed to this subject, I will give you one problem tomorrow. You solve and tell me the answer. If you are not getting, I will tell you the answer, because on your own doing, I think you will really understand everything. Okay.